All right, so a Hamilton cycle is a cycle that goes through every vertex of the graph. So the vertices of the cycle are the vertices of the graph. So it's different than an Euler-Tor because you're allowed to skip edges. We're going to say a graph is Hamiltonian if it has a Hamilton cycle. So one of the good things about the study of Euler-Tors is that we have an if and only if theorem, that there's an Euler-Tor if and only if every vertex has even degree. Turns out to date there is no such criterion for the property of being Hamiltonian. All we have instead are necessary or sufficient conditions. Here are some necessary conditions. So if these conditions are not met, you're guaranteed your graph is not Hamiltonian. 1, the graph must be connected, and that's because if your graph had two different components, then it's not possible to get a cycle that contains every vertex of the graph because you would have to be able to cross from one component to the other. Similarly, G has no cut vertex, and the reason for that is because suppose G did have a cut vertex, and any cycle containing this cut vertex V has to be entirely contained in one side or the other. So you're not going to be able to get a cycle that goes through every single vertex of the graph, because any sort of walk that covers every vertex at least once has to go through this vertex an even number of times, at least 4 times. And so every vertex can only appear on a cycle exactly once. Finally, the minimum degree of your graph has to be at least 2. If you have an isolated vertex, then you're not connected. And if you have a vertex of degree 1, then it's sort of what they'd call a pendant edge. It's like a leaf for a tree that we'll see later. And the obvious issue here is that you can go to this vertex, but you can't leave it. So it can't be part of a cycle. So now we'll discuss some sufficient conditions. The first one, known as Dirac's theorem, says that if the minimum degree of the graph is at least n over 2, n is at least 3, and G is a connected graph, then your graph is Hamiltonian. Note that sometimes this is stated as saying if every vertex has degree at least n over 2. But these are equivalent statements. The other statement is called Orr's theorem. Again, n has to be at least 3, and G has to be connected. The new statement is that for every pair of vertices that are not adjacent, so they don't have an edge between them, if their sum of their degrees is at least n, then G has to be a Hamiltonian graph. The condition that the graph has to be connected in both cases makes sense. The fact that we require there to be at least 3 vertices has to do with the fact that the only connected graph on 2 vertices is an edge, and clearly you can't make a cycle with only one edge. All right, so we're going to prove the contrapositive to both these statements. In other words, if G is not Hamiltonian, then it's either disconnected, n is strictly less than 2, or the other condition has to be violated. So that means for Dirac's theorem, there exists a vertex whose degree is less than half the number of vertices. And for Orr's theorem, we're proving that there exists 2 non-adjacent vertices where the sum of their degrees is strictly less than the number of vertices. So this is kind of unusual that we're proving 2 theorems at the same time, but that's because the most common proof strategy for Dirac's theorem and Orr's theorem is the same. So first, suppose G is not Hamiltonian. If you have fewer than 3 vertices, or G is disconnected, we have nothing left to show, because those are 2 of our 3 conditions. So we're going to suppose then that n is at least 3 and G is connected, and then we want to show our other 2 conditions hold. That there's a vertex whose degree is less than half the number of vertices, and that there's a pair of non-adjacent vertices where the sum of their degrees is less than the number of vertices. And so here's going to be our strategy. We're going to let P be a maximum path of G. With endpoints, we're going to call U and V. So we're going to write P as x0 through xk, and then U is the name of x0, and V is the name of xk. Note here that we are talking about maximum instead of maximal, so we want the longest path possible. So we're going to rely on the following lemma. If you take the induced subgraph on the vertices of your path, and the result is Hamiltonian, then so is the original graph. So here's our proof. We're going to let C be a Hamilton cycle for this induced subgraph. We're going to write the vertices in order on the cycle as y0 through yk. Note here, I'm not making any assumptions about how many of these edges came from our original path, by the way. And first off, we're going to suppose that the vertices of the path do not equal the vertices of the entire graph. So let Z be some vertex on G that's not on the path. Since G is connected, there has to be a path in our original graph from Z to U. We're going to let the vertices on that path be denoted Z0 through ZL. We're going to let I be the first index, where Zi is on the original path. So the point is we have our path P here. We've taken a vertex outside the path, and we know we have to be able to connect it to U. We're letting Zi be this first point here. And the reason why we do that is because then we have this edge to Zi minus 1. And then we remember that somehow this path is also a cycle. And so this Zi appears somewhere with Zi minus 1 outside it. And so then the idea is that we're going to ignore this edge, go down and around the cycle and create a longer path. So Zi minus 1 Zi, we're going to let Zi be equal to Yj, where Yj is some vertex on our cycle. So then Zi is Yj, then we can go to Yj plus 1 all the way to Yk. Since we have a cycle, Yk is adjacent to Y0, and you can go all the way to Yj minus 1. And the point here is that the number of vertices, Y vertices, is the same as it was before. It's the number of vertices on the path. And we've just added one more vertex. So we have a longer path than P, but P was supposed to be maximum. So the only thing we can conclude is that every vertex in the original graph is actually on the path already. And thus G is Hamiltonian because the Hamilton cycle for P is the Hamilton cycle for G. So thus we are reduced to having to show that the vertices on the path form a Hamilton cycle. If they do, then we're done. Now the fact that our graph is Hamiltonian says that the vertices on the path do not form a Hamiltonian subgraph either. And so this tells us many things. For instance, when we're looking at our path from U to V, we see that we cannot have the edge from U to V because then we would actually have a Hamilton cycle right there. And that's exactly what this step is saying. If you had the edge from U to V, you can tack U onto the end of your path and you now have a cycle. So for the contrapositive to Orr's theorem, these are going to be our two vertices. So we need to show that the sum of their degrees is less than the number of the vertices in the original graph. And to do that, we're going to create the following two sets. We're going to let S be those xi, such that x0, xi is in edge of the graph. Notice by maximality of the path, all the vertices that are adjacent to U have to be on the path. And so S is just the neighborhood of U. T, it turns out to get this proof to work, is not quite the neighbors of V. What we do is something slightly different. We take vertices on the path where the vertex straight to the left is adjacent to V. So we're taking the neighbors of V, and then we're going one to the right. And that's the vertex we put in T. And so we're going to claim this intersection of these two sets is the empty set. And the reason why is as follows. Suppose that there was a vertex in the intersection, then that means this xi is adjacent to U, and xi minus 1 is adjacent to V. And so then it turns out you can create a cycle by deleting the edge from xi minus 1 to xi. In particular, you go along the path till you hit xi minus 1, then you jump to the end of the path and go backwards till you hit xi, and then you jump back to the beginning. And so you do get a Hamilton cycle in this case. And since we're assuming our graph is not Hamiltonian, it follows that this shouldn't be possible. And thus, this intersection must be the empty set. Notice that the size of the union is equal to the sum of the sizes minus the size of the intersection. Since the intersection is the empty set, that means the size of the union is the sum of the sizes of the two sets. So now we're going to get our counterexample for Orr's theorem, where he claimed that the sum of the degrees of u and v is strictly less than n. Since p is a maximum path, all the neighbors of u are on the path, and all the neighbors of v are also on the path. As discussed, the neighborhood of u is S, so the degree of u is also the size of S. On the other hand, since every vertex in T is one to the left of a neighbor of V, it follows that the size of T is also equal to the degree of V. And so when we add these two degrees together, we get size of S plus size of T, also known as the size of S union T. By claim 1, U and V are not adjacent, and so in particular, we know S union T can't contain the entire path of k plus 1 vertices, so it's actually got to be strictly less than k. And since k can be at most the total number of vertices, we then see that we have our strict inequality. So our sum of degrees is strictly less than n. We still haven't given our counterexample for Orr's theorem. For that one, we're going to claim that the degree of one of the two endpoints of the path has to be less than half the number of vertices. And how we do that? Well, one of these vertices has to have smaller degree than the other. So without loss of generality, let's assume the degree of u is less than the degree of v. Then that means twice the degree of u is less than or equal to the sum of the degrees. As we just saw, the sum of the degrees is strictly less than n. So if we divide by 2, we get that the degree of u is strictly less than n over 2. Similarly, if the degree of v was smaller, then we would get that the degree of v was less than n over 2. Either way, we found a vertex whose degree is less than half the number of vertices. I should note that even though we stated this in terms of contrapositives, it does actually give an algorithm for finding the Hamilton cycle in the cases that these degree conditions work. And in both cases, the Hamilton cycle is given by finding a maximum path. And then if the two endpoints form an edge together, it turns out you're done, because as we had already noted, that maximum path, now you have a Hamilton cycle for the path, and that cycle ends up being a Hamilton cycle for the entire graph. Otherwise, it turns out due to the sum of degree conditions, the intersection of S and T has to be non-empty, so you can just go down the path until you find a vertex adjacent to the endpoint whose neighbor is adjacent to the starting point, and now you have your cycle. Notice, of course, that this relies on being able to find a maximum length path, and that's actually the next topic, about finding the shortest length paths between any pair of vertices, so you can use that algorithm to find the longest path possible.